Hello everyone. So last video we talked about approximations. Approximations of definite integrals, such as the left and right Riemann sums. Left and right Riemann sums, the midpoint sum, and the trapezoid. Trapezoidal sum. Okay? So, these are approximation techniques. However, today we're going to be learning a really important theorem, a really important rule, a very fundamental rule. Okay? And this rule, so let me just delete this. This rule is quite appropriately called the fundamental theorem of calculus. And just by the name, you can see how important this theorem is. Okay? Because it basically defines the definite integral and connects it to the indefinite integral and allows us a way to evaluate definite integrals exactly. And the fundamental theorem of calculus basically says that the definite integral from a to b, or let's just make b to a, is from a to b of f of x dx, that is equal to big F of A minus big F of B, where big F of X is the antiderivative of F of X. Okay, so if you were to integrate F of X as if like when you would take an antiderivative and then evaluate the function at A and subtract the antiderivative evaluated at b from that would be the value of your definite integral. Okay? So this is the fundamental theorem of calculus. Okay? And this is so important because now we have a direct link between indefinite and definite integration and allows us a way to find definite integrals exactly. We can integrate the expression, then we can find the integral exactly and find an exact representation rather than an approximation, which we have been doing. So let us do an example, okay? What is the integral from 5 to 2 of x squared dx? Okay? So rather than resort to an approximation technique, let's take the antiderivative of this term, the indefinite integral. So that would be x cubed over 3, use the inverse power rule. However, so how I would write it, you would put your limits of integration, 5 and 2, like this. And you would basically do 5 cubed, because x is 5, over 3 minus 2 cubed over 3. So you have f of 5 minus f of 2. Okay? And if you were to evaluate this, you get 125 over 3 minus 8 over 3. And that gets us 117 over 3. And now, using this fundamental theorem, we can find area exactly without using a limit process, okay? So let's find the area of a trig function, okay? So let's find the area inside one of the arches of sine of x. So this is f of x equals sine of x. F of x equals sine of x. What is the area of inside one of these arches? So what is the area of the shaded region? So the region I'm shading in red. Okay, so we defined the definite integral as the area under the curve on the interval from A to B. So A is obviously 0, okay? It starts at the origin. That's when the shaded region starts. Where does it end? Well, it ends over here when sine of x equals 0 again. And that happens when the next value where this happens is x equals pi. Okay, because sine of pi equals 0. So we're basically taking the definite integral from 0 to pi of sine of x dx. And with the fundamental theorem of calculus, we are able to evaluate f of pi minus f of 0, where big F is your antiderivative. The antiderivative of sine of x is negative cosine of x. So negative cosine of x, and we just evaluate it from pi to 0, okay? And that gets you negative cosine of pi minus negative cosine of 0. And negative cosine of pi is negative 1, okay? Cosine of pi is negative 1. And we get 1 from that. Cosine of 0 is 1. So you're subtracting negative 1. Remember this negative sign. So you have 1 plus 1 is 2. So the area under this red arch, this is 1. The area of this red region is exactly 2. Okay? It's exactly 2. Now, as you learn to do more and more integration techniques, you can evaluate a more varied type. Okay, lots of varied types of integrals. Okay, integration is usually a lot more difficult than differentiation, though. Okay, so finding areas will be a bit more difficult, but still doable for many functions. Now, turns out there's a second part to this fundamental theorem called the second fundamental theorem of calculus. Fundamental theorem of calculus. The second fundamental theorem of calculus. In order to understand the second fundamental theorem, we're going to have to talk about functions that can be defined by an integral. Defined by a definite integral. So for example, let's consider the function g of x equals the integral from 2 to x of f of t dt. Okay? So here, the function g is defined by an integral expression. So it's not explicitly given. Okay? So this basically equals big F, or big F's our antiderivative, of x minus big F of 2. Okay? And what we can do now is, using this, we can easily kind of come up with a conclusion of the second fundamental theorem of calculus. So when we began with indefinite integrals, we said that the derivative and the indefinite integral were polar opposites, or inverse operations, basically. Okay? Now, I want to see if we can extend that to a definite integral. And that's basically what the second fundamental theorem of calculus does. Okay, and this one's not hard to prove. So let's define a function g, similar to the one we defined above, except we have an arbitrary constant over here. So we're taking the integral from x to a of f of t dt. So from the first, I can call first fundamental theorem of calculus, this integral can be evaluated as f, big F of x, or big F is the antiderivative, minus big F of a. Okay? So if we take the derivative of this, we get the derivative of big F of x minus big F of a. And big F of x is an antiderivative, and we've shown through the antiderivative and differentiation being inverses, kind of like inverses, that this would just be equal to f of x. It would reverse this back to your normal function. Okay? Because we're taking with respect to x. So if f, big F of x, and the derivative of an antiderivative will always be the original function. So that'll be f of x minus f, big F of a. Now a is a constant term, so this is also a constant. So that'll be 0. So we can conclude, okay, that the derivative, this is basically the second fundamental theorem of calculus. The derivative of the definite integral from x to a of f of t dt, where f of t is any, like, any function, that is always equal to f of x. So it kind of mirrors, it kind of establishes a link between differentiation of a function defined by a definite integral. Okay, let's do a couple of practice ones. So let's evaluate this expression from 2 to x of sine x, okay, sine t squared dt. Now from the second fundamental theorem, since this is constant, this is x, okay, we can just replace this with sine of x squared. So this is not hard, okay, until you start to change some of the limits. Let's define a function h. H of x equals a definite integral from x squared to 2x of f of t dt. Or in more generally, a function of x, so x squared or 3x or sine of x, any function of x, to another function of x. How do we find a derivative of that? Okay, so let us find a derivative, and we have, if we use the first fundamental theorem, this equals the antiderivative of our first function of our first limit, which is a function of x, minus the second, the antiderivative evaluated at the lower limit as a function of x. Now, if we take the derivative of that, well, the derivative of an antiderivative will just be the original function, okay? However, you have a function of x inside of here. So what makes sense is to use the chain rule, okay? So if we take the derivative with respect to the inner function, we get the original function evaluated at the inner function. So your initial function, small f of u of x, but you have to take the derivative of the inside function with respect to x as well. So you get u prime of x, okay? And you could do the exact same thing over here. F of v of x, small f, times v prime of x. You're just applying the chain rule. Chain rule. So a more general version is that the derivative of a definite integral where the limits are functions of x, the derivative with respect to x of this integral f of t dt equals f of u of x, u prime of x, minus f of v of x, v prime of x. Okay, this is another formula that is helpful to memorize. Of course, you can derive this just by using chain rule, okay? So let's see what I actually mean by functions of x. Something like this is a situation where I would be using this other formula, okay? So let us consider the function g of x equals the definite integral of x squared to pi of sine of the square root of x plus 7 dx. Or actually, let's change the variable. We have to change the variable. Okay, so this variable can be the same since we have functions of x as our limit, as the limits of integration. Okay? So let's first find g prime of x. Now we have a function of x over here. Okay? So we would just plug in the original function, plug in the original function in t, and then multiply by the derivative of the top function. And since the bottom function is a constant, okay, this is a constant term, that will just be 0. Okay, so we ignore that. So our final derivative is 2x sine of x squared plus 7. Okay? So let's do another. Let's consider the function. Let's consider the function h of x equals a definite integral from x cubed to 2x squared of, let's do the square root of t squared plus 6t minus 1 dt. Okay, so let's find h prime of 1. So how do we do this? Well, let's just first find h prime of x. Okay, so that will just be, so we have two functions of x. Okay, So the formula, I'm just going to write the formula. So the formula equals f of u of x times u prime of x minus f of v of x times v prime of x. So if we were to apply this formula, you'll get f of u of x. So wherever there's a t over here, you just replace by x cubed. So x to the 6th plus 6x cubed minus 1 times the derivative of the top function, 3x squared, minus 2x squared, so that would just be 4x to the 4th, 2x to the 4th, 4x to the 4th, plus 6t. So 12x squared minus 1. All that, I'm just going to put the multiplication over here, 4x. So our final derivative equals 3x squared times x cubed plus 6x, x to the 6 plus 6x cubed minus 1 minus 4x times 4x to the 4th plus 12x squared minus 1. And if we were to take h prime of 1, which is what we were asking, we just have to plug in the value. So we have 3 times the square root of 1 plus 6 times 1, 6. So 1 plus 7 is, 1 plus 6 is 7, minus 1 is 6. Minus 1 is 6. Minus 4 times 1, 4 times the square root of 4x to the 4th, so that's just 4, plus 12 times 1, that's plus 12, minus 1. And as a result, we get 3 square roots of 6 minus 4 plus 12 is 16, minus 1 is 15, 4 root 15. So our final answer, h prime of 1, is 3 root 6 minus 4 root 15. So as you can see, these theorems are not really that hard, okay? Although they're incredibly useful. Functions defined by definite integrals appear basically every single year on the AP exam, and in most calculus tests. Tests can ask you about functions defined by definite integrals. So it is very helpful to have the second fundamental theorem mastered and, well kept in your memory. Okay, so you can apply them easily. Thanks for watching. If you have any comments, please ask. If you have any questions, please ask them in the comments. Make sure to like and spread this video.